So, hey, my name is Marcel, that has already been said, and today I want to talk a bit about AI agents, what they are, and how they actually work, when you want to use them, and whatnot. So, before we start, actually, about this topic, I need to do a bit of a promotion of my company where I work. So I work at KINIT, which is the first and still the only independent research institute in Slovakia, conducting application-oriented basic research, supported by private sector. And besides basic research and applied research and development, we help companies either with various collaboration or different activities to take the results from research and transform them into innovative solutions. So simply put, we do tech transfer for them. We also have a booth out there, so feel free to check us out once we are done in here, if you have any questions regarding KINIT. Or even if you don't, just visit us. We don't mind. So now let's get back to the topic of AI agents. So as you may, all of you already know about LLMs and what they are. You should be rather familiar with them, and they do in fact contain a ton of world knowledge. It's quite impressive how many information they can retain just from training alone, but they have a ton of shortcomings associated with them. And so you might think that because of these shortcomings, LLMs are not necessarily the best in terms of providing relevant factual information or responses to your questions. And in certain sense, it may be true. And that's why we need a way of providing LLMs with some additional knowledge, some factual or relevant data, and inject some external knowledge pertaining to a specific question, so that we can bias the model to respond the most truthfully, based on some factual information. So for this, we use some kind of external knowledge. And we differentiate between two types of external knowledge. We have knowledge bases or tools. Let's start off with knowledge bases. So for those, we can use, for instance, a Retrieval-Augmented Generation. You have an example of, for instance, if you want to implement a chatbot in your company that would work on top of company policies, documents, and other data. You would want it to know all that information about your company. And we suppose that the amount of data is non-trivial, meaning that you can't simply naively put all the data into the context. And so that's why we need to perform the RAG, Retrieval-Augmented Generation. Simply put, what we do is we embed and store all the data in vector database. And then we use semantic search to retrieve the most relevant data, the most relevant documents pertaining to your particular question. And that is subsequently fed into the model context. And once we have it in model context, we can use it to condition the final response of the model, so that it uses and it is biased by that particular information that is relevant to user query. Then moving on, we've got tools. So a good example of some tools could be a web search tool or an SQL tool, where you have, for instance, in terms of SQL tool, you have some abstraction over your SQL database that would allow you to work whether to read or write some data into your database. And unlike knowledge bases, tools are used not only to retrieve information, but also to interact with the environment and perform write operations. So since we are talking about tools, two things are necessary and are in order to mention, and that is tool calling, or MCP. We will be talking about MCP later on at the end of this presentation, so let's now focus on the tool calling itself and what it is. Because most of you might already know that since LLMs are only language models, they only generate text autoregressively, meaning that they can't actually call any tools. And so we need a way how to enable LLMs or some process how we can actually manage to call tools. So what we can do is perform so-called tool calling, also known as function calling. So those two terms are interchangeable. And basically what we do is we first of all pass some tool schemas associated with each tool that we want to give LLM to. tool schema, which represents how the tool actually looks like, what the tool name is, what tools arguments are. And once LLM has an information regarding all this information, it knows that it has in its disposal a possibility to an option to actually call a specific tool. What it does is perform said tool calling, meaning that it generates a JSON schema, for instance, that specifies what tool we wish to call, together with actual argument values. So not only, because in the tool schema itself, we only have information regarding like what the data type of each individual function argument or tool argument actually is, whereas here in the tool call, we actually have corresponding values. And so once we have this, a tool call, which is still a part of LLM, and that's what LLM responds with. And now we need a way of translating this to an actual tool. And this is something that is being done, let's say, in background, in various frameworks, implicitly. And so we perform some, for instance, actual function associated with that tool. Okay, but till now, we've been talking only about some concepts, but not necessarily about AI agents at all. So let's rectify that and talk about them. So what are AI agents? They are an LLM-powered system that can decide its own next steps, calling various knowledge bases, tools, or whatever, instead of following a strict fixed pipeline. So the highlighted part is there in purple, the most important thing being that it decides its own next steps. Because the AI agent can be also thought of as a so-called thought, action, observation cycle, where we have three concepts, let's call it that way, thought, action, and observation that alternate between each other. And we start off with, say, a thought, when an agent may reason about some things, and then it can interact with the environment, call tools, and then get those responses from those tools back to its context. And then, based on those, it can be conditioned whether it wants to further continue or not. Because as you can see, there's a loop, actual loop in between an agent and the environment. And so this potential loop that I've just highlighted can be theoretically run indefinitely. And so here we've got an example of a very simple sequential diagram, sequence diagram, where we visualize how an agent interacts with the environment in order to get a very basic response to a very basic question. It wants to, first of all, access environment a specific tool. So let's quickly go over all these messages in this image. So we start off with an initial question. A user may ask a specific question to an agent, and together with the particular user question, there's also a system prompt that biases and conditions the agent to work in a certain way. But that's actually not something that the user specifies. That's something baked into the agent itself. Then we may have an optional step of creating a plan. It depends on how you prompt the model, whether you want it to do some additional reasoning before each step it takes or not. And then we have, since the agent deemed it necessary to interact with the environment and call a specific tool for performing web search, it did so and performed a tool call. And it wanted to call a tool called Tavily search. So now within the environment, an actual function is called in order to get some results regarding my query, whether like what the top 5 most popular songs are. And then we get a response to the model from the environment, the response associated with that particular tool. And once we have that, we can either an agent can yet again have an optional step of reasoning whether we are done or whether we want to go for another run of this loop, or whether it is satisfied and has sufficient number of information for the user request to be satisfied. And in this particular example, we've decided to simplify the process by showcasing that that's done and just let model respond. Okay, so associated with AI agents, LLMs, and whatnot, there are tons of frameworks, and due to the limited amount of time we have, we will quickly run through them. So when we start working with AI agents, we have a few things we need to consider. First of all, there are various frameworks for serving LLMs or techniques. We need to decide whether we want to deploy them locally and serve them locally or remotely. Once we have, because the heart of the AI agent is always an LLM. Once we have that, then we have various frameworks for building AI agents. Whether we have some more bigger frameworks like LangChain or Llama Index that are apparently considered to be more opinionated based on some people, based on the community, or we have smaller libraries that are more lightweight, like small agents, OpenAI, Agents SDK, or Pydantic AI, that try to minimize the abstractions that are found within those respective frameworks. And for the sake of this presentation, and also in Kinit, we've quite adored Pydantic AI due to its lightweight size, let's call it that way, and also its simplicity and easy to use. So now, on the next slide, I want to quickly go over some basic things, how you can set up your agent or perform some tool calling and structured output. So here, we have a snippet of code where we define an agent. It is very straightforward. You specify what model you want to use, what the system prompt is, and then there's also, besides tools, a so-called output type argument. This output type argument specifies what the structured output of the model should be, what the model should adhere to in terms of like some kind of output schema. And here we have an actual Pydantic model. Just a quick note, Pydantic AI, you could have guessed that it was developed by the same team as the Pydantic library itself, and so they heavily rely on things like Pydantic models. And you can use this model directly within the output type to specify what the formatting of the output of the LLM should be. And so once we actually look at the response of the model, we see that it actually conforms to the specified schema. It's a list of best songs. Next, we've got tools. Tools can be either some predefined tools readily accessible in the Pydantic AI itself. For instance, the Tavily search tool is there by default, or you could create your own tool. Here in this example, this tool does nothing because it's a magic tool and magic doesn't exist, so that's why it doesn't do anything. But once we take a look at the actual system prompt, or a part of the system prompt that visualizes what tools this particular model, this particular agent has an access to, we see 3 tools actually available. Besides those first 2 that we specify in the tools argument, we also have a so-called final result tool, which simply is used for proper mapping of the output. Still, AI agents have many drawbacks. They're cool and all, but they may behave unexpectedly. You see, the more loops are performed within communications between the agent and in the environment, their context keeps inflating, and with each new step performed, they can get overloaded with information. We don't have some fine-grained control over agent behavior, and hence it's hard to inform some strict path. And so a question arises as to why shouldn't we simply, model the behavior ourselves? That would be simpler, especially in some cases where we actually know what the task is, how we can actually set it up in a way that we would be satisfied with. Because if you have a situation where you employ an AI agent for a task where it actually goes away from the ideal solution you would normally associate with that task, that, and the task and the solution to the task yourself, well, might as well implement it yourself. So, and that's the idea of a workflow. In workflows, we define the control flow rather than leaving it to AI agent. And so now every run follows the same path. It's easier to debug and reproduce. There are some prerequisites associated with implementing workflow. Obviously, we need to know the strategy, how to solve your task, because if it's something that you can't even begin to comprehend or know how to solve, then you're better off using an AI agent. So if it's something that you can easily, tangibly implement yourself, you have an idea as to how you want to have it implemented, simply go for workflow. And you don't need to bother with AI agent coming up with different solutions that are simply perhaps too contrived. A good example of a workflow is, for instance, WikiChat, which is a web search workflow. There's also a paper to this, and they try to balance creativity and truth. They try to leverage LLM's natural fluency and its creativity while constraining it with verifiable knowledge. And so that's why there are a ton of steps that utilize things like Wikipedia or fact-checking in order to balance the output what LLM generated and what is actually true. And we could theoretically ask an AI agent to do all these steps on its own. And this is something that I asked ChatGPT to quickly come up with. I didn't even read this, so it's quite possible that it is a stupid thing, but still, it tried to mimic, let's say, WikiChat to a certain degree. And you could come up with a very specific system prompt that specifies all the steps necessary to be taken in order to mimic Wikiflow or WikiChat or whatever that workflow's name was. Or, but still, the biggest problem is that even if you specify system prompt to the greatest detail, to the minute detail, how do you actually enforce an AI agent to adhere to this predefined pipeline? You can't. And so that's the biggest problem. And so both of these terms or things, concepts, are sides of the same coin. We've got an agent and a workflow. Both of them have their own advantages and disadvantages. And you need to know what you want to use, depending on what the task is. And so now the question arises as to why shouldn't we simply combine the best of both worlds? We've introduced two concepts that are sort of contradictory to each other, yet we could combine them in a way that we would use the flexibility of an agent, but also a fine-grained control of a workflow. And so we would come up with a multi-agent systems. So what is a multi-agent system? So unsurprisingly, it's a system where there are multiple agents. Who would have thought? So there are multiple specialized agents that collaborate, each responsible for their specific part of the task. There are some basic concepts that multi-agent systems are based on, for instance, on task decomposition, because you may have a task that you want to do, but you need to, first of all, decompose it to smaller subtasks that you could assign to individual specialists, individual LLMs, agents. And the nice thing about this is that you can modify each agent to be specific to your demands, to your specific subtask. Each agent can have a different LLM, prompt, context. And we wish to go over two orchestration patterns today. And that is agent delegation and agent handoff. Starting off with agent delegation, it is a centralized orchestration pattern with a router that delegates tasks to specialists and consolidates the results. And specialists are then defined as tools for the router that may invoke them. So you could think of this as some kind of extension of an AI agent. Why is that? Because here we've got a simple diagram of an agent with all those things like thought, action, and observation. And there are tools which could be represented, or tools are the environment itself that an agent works with. And now agent delegation is simply put this. We allow tools to also be represented as agents. And that's mostly it. There's nothing really special about it. It's just a fancy name. And once you have this, a router is freed from doing all the work because the router outsources tasks to specialists specifically tailored to do their own task. Now a router can only focus on its own job, and that is to manage specialists or steer the conversation between the user or any other third party, depending on where your system is employed as. And also, we separate task-specific context from general context. Because for instance, when we do a specific subtask that a specialist is responsible for, we we usually don't need that information, all those messages that a specific subagent works with and creates with other services or tools to be flooded back to the main router, main agent. Sometimes it is necessary, and if it is, well, you will set it up in a way that all the messages would be sent back to the main router, but usually you want to abstract these things, and so essentially you want specialists to only return the actual results to the task they were given. And so once you do this, you also make the context of the main router much shorter, because you get rid of other tool calls that might have been called and performed by the specialist. Then moving on, we've got agent handoff. This design introduces AI agents into a workflow. So unlike the previous agent delegation, where it was more like an extension of an AI agent, this is an extension of a workflow. Because yet again, even though it may sound somewhat fancy, agent handoff, what it is, who knows. Essentially, what we simply do is by having arbitrary workflow, we replace individual LLM calls by agents. And that is it, because we simply want to have and pass and hand off the responsibility of one agent to another. And that's about it. Obviously, like each agent in this diagram, agent 1, for instance, could be actually a multi-agent system. But at the end of the day, there's one main router, one main agent that behaves as some kind of interface within this pipeline. This orchestration pattern is decentralized and performed like programmatically. This handoff is not chosen by performing tool calls, but rather you simply specify it in your code, and that's it. It's yet again based on the ideas of task decomposition, because you now need to specify your task or divide it into a sequence of subtasks, and context may be shared among agents, depending on our setup and the task you wish to work with. For instance, perhaps you would want all the past messages that agent 1 have done with other tools to be also available to the agent 2. Perhaps not. Perhaps you only need the actual response. Perhaps it's too much of, and there are a ton of messages, so you perhaps want to perform some summarization first before moving on to the agent 2. Okay. And now we will take a look at the way how we can actually implement these multi-agent systems in Pydantic AI. And so you could imagine a very simple deep research system composing of 3 things. We've got a router. It's an agent talking to user, retrieving necessary requirements, and then a web search. An agent expanding user queries, like creating multiple synonyms or synonymous queries that would be used for searching the web. And then we have summarization, an agent that summarizes the retrieve results of the web search agent and give us some concise report. And so let's start off by looking at the implementation of our specialists first, because we will take a look at the agent delegation first. And so this is the implementation of these 2 models, or agents, if you will. And they're mostly guided, and their functionality is primarily biased by the system prompt itself. Next, we will take a look at how we can actually integrate them into the agent delegation pattern. And so we have 2 functions, because we first of all need to wrap each agent into its own tool call. And as we can see, each of these functions represent a very simple wrapper around the agentic invocation. And then we use these 2 tool calls within the router agent itself, so that it has an option, a capability to call these 2 functions or tools, if you will. And I wanted to quickly emphasize this thing, what I've done, and that is I intentionally decided not to pass along the response of the web search agent, to the router agent, but rather decided to store it to a separate file. And why is that, you may wonder? Because, well, it also depends on the task. Everything usually depends on the task itself, and then you can optimize things based on your requirements and demands. But At the end of things, at the end of the day, I completely lost what I wanted to say. Regardless, let me get back on track. The idea behind storing the result here in the file itself is not to sully the main router context. Because if we were to pass it along to the router may or may not actually need that information, all the data, all the documents associated with the web search. And so we should rather store it in some persistent storage, and then we can use it later on depending on whether we need it or not. And so what we do here, this actual tool, the upper one, only returns a file path to a specific file that should contain all that information associated with a web search. And then we use that specific file path in the second agent, the summarization agent, that reads the file and then can use it for performing summary. And the nice thing about this is that due to this approach, we never needed to actually pass, let's say, imagine a few pages long information regarding what results, search results were associated with that particular user query, but rather saved it separately in a file system, or we could have had it in a variable. It doesn't really matter. Some kind of persistent storage would be nice. And then we simply use it on demand. And there's also a question regarding, like, okay, but router may need that information later on down the path. So ideally, what we would want to expand this code with is by specifying within the router itself additional tool that would allow it to also interact with file system and have a possibility, an option to actually read that specific file. But for the sake of visualization, we decided it would be best way to simply write it and read it in the code itself, but we could have easily specified those file system tools within each of those specialists as well, so that we wouldn't need to actually implement the logic of writing and reading files ourselves. Okay, and now we will take a look at agent handoff, which is even simpler than the previous thing, so it will be even better and quicker. So just for the sake of keeping the consistency the same, we decided not to change the names of the agents, but still, this is not a router agent anymore. It's more like a main agent or the initial agent that interacts with the user in our potential pipeline. And we still wish to work with those three models, agents, for web search and summarization, but now instead of having one router agent, one main agent, we have a sequence of three agents that we will be working with. And for the sake of making this example work, what we have done here is we specified an output type for this router to be simply a string, a topic. And now this is it. This is the agentic workflow, the agent handoff, if we will. Simply put, you programmatically decide what the workflow, what the pipeline is supposed to be. In this particular case, it's simply three agents in a row. And so it looks like 3 lines of code, and that is it. Very simple. But there are also some drawbacks with multi-agent systems. For instance, once we get into them, they may cost more, and there's also problems with latency due to the fact that you have multiple agents you need to work with, multiple LLM calls, perhaps more tokens, etc., etc. But more importantly, because this could be also justified to a certain degree, because you may say that you have multiple agents, so it may cost more, but not necessarily, because if you set your task in a way that you would be able to optimize it, especially if you were to compare it to a simple AI agent, then you could have a case of using a multi-agent system in practice. The bigger problem is a complex coordination, designing and managing roles. There's a ton of engineering overhead that is associated with multi-agent system. So you may start off with implementing an AI agent or workflow first, and then you can go into multi-agent system depending on whether your task, your solution actually needs it. So depending on the task, if it's simple, it may be an overkill, but usually the best practices would be to start off simple, an AI agent or workflow, and then you can move on to multi-agent system depending on your needs. You need to choose right LLMs for specific tasks, especially if we talk about workflows or multi-agent systems, then you have an option to actually specify and choose a specific sized LLM for each LLM invocation or an agent loop. And you need to define clear goals, what your task is, be specific with your task definition, especially when you create your system prompt, do task decomposition if it's necessary. And if you start doing task decomposition and it is like a good thing, like it makes sense, you might as well go into workflow or multi-agent systems. You also need to have some kind of evaluation or testing to compare different systems, create an evaluation data set, or have some observability tools so that you can check whether everything works the way it's supposed to. And the evaluation data set speaks for itself. You may have multiple ways how you can implement one thing, and now how can you actually identify and recognize what the best approach is? You need a way of objectively identifying and evaluating quantitatively what the best approach is for a specific task. And also managing and optimizing agent context to reduce costs, like things like what information to retain from past system stages and interactions, or where and how to store the retrieved information. This alludes to that previous slide where we had the information stored in system file rather than passing it to the context. And these things tackle the problem of context engineering. We unfortunately don't have that much time to go into this, but there's also like one big domain that has been like lately being focused on. Okay, and we've got last two slides regarding MCP, and then we will be done with plenty of time to spare. So, what is a model context protocol? So it's a protocol that standardizes how LLMs connect to external tools, data sources, or services. And so now you have a term called MCP server, and you might be wondering what that is, or you may already know that. And in that case, well, why am I even here? But still, it contains a list of tools with their associated tool definitions that any arbitrary LLM can call upon. And then those tools wrap some actual API logic of the service. A good example would be, for instance, these particular screenshots associated with an official GitHub MCP server. And this one provides a list, actual multiple tool sets of various tools that you can use within your LLM. And just to shed a light on one particular tool, we see a so-called create issue tool that has its own description together with a ton of arguments that are also described so that all this information is passed to the system prompt, and LLM can see this and then properly fill those arguments. And what the create issue actually does most likely is that it calls some SDK inside that implementation and calls the GitHub API. And a bit more information and details about MCP. So in regards to architecture, we recognize three things. We have MCP host, client, and server. Let's start off with an MCP host. Those are either, let's say, IDEs or some agent frameworks. In our example, it's Pydantic AI framework. And then, on the other hand, we've got an MCP server that we've already discussed. It contains tools and resources that an LLM can access. And then there's also an MCP client that, for the sake of this presentation, you can simply think of it as some kind of middleman that manages the conversation between the MCP host and MCP server. And defaultly, or by the rule, there's a one-to-one mapping between an MCP client and an MCP server. Okay, and now we have two options as to where we want to deploy our MCP server, either locally or we can connect to a remote server. And depending on where we want to host that MCP server, we use a different kind of transport protocols. But I'll try to quickly wrap this up so that we have actual time for questions. So here we have like three ways how you can implement the MCP server within your Pydantic AI framework. You can either run it remotely or locally. If you run your things locally, you have an option of using either HTTP protocol or standard input-output. And if you choose to go for these standard input-output, the actual implementation or what actually is being done in the background is that we don't have an API server per se, but rather there's a sub-process that is run under the actual process that invokes that MCP server using that protocol. Okay, and that's it. We're done.
Presentation. We have 6 questions here. So, how do you handle cumulative errors in agents?
That's a great question. There are multiple ways how you can do this. Like the more naive thing that we could rely on is, for instance, in Pydantic AI, once you get an error, you will automatically feed back that error to your agent so that it can try not to do that anymore. You also need to have some way of limiting the number of loops that your agent can do. Otherwise, you will need to pay quite a hefty amount of money at the end of the month, depending on where you have it set up. And yeah.
Question number 2, could you please provide a couple simple, small, and self-contained use case examples to use to familiarize oneself with practical agent implementation? Ideally, something general enough to be useful in a wide array of situations.
I suppose like the deep research example that we had in our presentation is sort of like a general concept that could be applied to anything, because essentially what you have are multiple agents that try to make the most out of information found on the web. And you could use this. You could also like implement this with one agent only, and that's also like. You know what? I like this idea of like try to mimic the deep research implementation by starting off with, let's say, one AI agent that tries to do all the thing, and you might end up getting into some trouble, perhaps not, depending on how complicated your task is. And then once you want to further like refine your specifications for the task, or just for the sake of learning purposes, you can then add multiple agents and try to play with that.
Wouldn't be the multi-agent costly?
Well, it depends on how you set it up, because you could either have one AI agent do all the work, but that would mean that it may do it suboptimally. If that's the case, it may do more actual work and more tokens would be generated rather than having more smaller agents that do things more efficiently. Not only can you actually specify and use smaller models for smaller like tasks, simpler tasks, but also they are more likely to succeed because you narrow down the task that they need to focus on.
Isn't a workflow similar to regular programming as we need to specify steps explicitly? What are then its benefits?
That's actually true. The workflow was perhaps a concept that tries to simplify the AI agent approach, I suppose. And that is like you still have LLM code, so you still use LLMs, but there's not necessarily that LLM doesn't do the control flow itself, so it doesn't have that feedback loop unless you implement it yourself, because at the end of the day, AI agent can be very simply reconstructed by you in the code, because what an AI agent is, it simply has an LLM, then a list of tools, and an LLM with a list of tools is still an LLM, and when would we draw the line between an LLM and an agent? Once it automatically processes the results from the environment or from the tools themselves, and then based on those results, it would do an additional prompting, and it would decide whether or not it is worth continuing either by responding to the user or doing another tool calls. So essentially, this is like a few conditions or loops that could be done on top of your LLM. So that's the main difference between a workflow and an AI agent. AI agent is more flexible because you can't really specify what it does. It's simply do things on the fly, whereas workflow has potentially multiple LLM calls that are, let's say, more naive. You need to specify and do a lot of fine tuning, so to speak. There's a so-called that fine-grained control, yeah.
Can you elaborate based on what the gate decides? It was on slide 26. Is the gate also an agent?
Usually the gate was simply some kind of condition, like whether the result is true or false or something along those lines. You can either go into branch A or branch B.
Is the agent core of AVS an alternative for Pydantic?
Actually, I'm not that familiar with Agent Core, but actually there are a ton of various libraries and frameworks, and all of them do the same thing usually. So it's all up to your preference, honestly, and where you are most comfortable with.
Thank you, Marcel. It's time up, so thank you very much for your presentation. If you like...